Okay, I think I'll start. Okay. All right, I think I might repeat some of this later. So this is, as some of you will know, this is a repeat lecture of SLT Low Road 2 for the recording, but I'm not going to exactly repeat everything. And to me, the sort of the value of the presentation is really because of the question that the audience ask. So I hope now that you have been through SL, like the entire what's it called, primer, you might follow the material a bit closer. Okay, I can. Yep. You can follow the material a bit closer, and you might have questions. So please do ask them when you do have them. Okay, so this lecture is about sort of a intuition building lecture. So we had the sketch of proof of free energy formula last Friday, but this lecture is more about building up the intuition and sort of getting to know what the various mode of degeneracy, what do we mean by singularity, what do we mean by degenerate critical points and things like that, and what their effects are to the quantities that we're interested in. Okay, all right, but first I just review some of the quantities in Bayesian learning, and this is to recall a lot of the notation. Right, so the setting is in Bayesian learning. So we usually we are usually given a truth model prior triplet. So we have Q, the truth, that's giving that is generating an RID data set for us. So DN is our data set, and each XI is generated, it's an observation generated from Q. P is our model, P of X parameterized by W. W is our parameter space, that's W, and each point is it's a model, and we have a prior over this parameter space. Okay, and we are familiar with this Ln notation now. It's the log likelihood. It's a negative log likelihood average over the data set. It's what we will typically think of as an energy or a loss. An energy would be a quick way of saying negative log likelihood, right? So I'll typically use that kind of terminology. And from that, we define something called the Boltzmann weight, which is just related to the posterior in some way. So it's, let me focus on that. It's, we give it a name, the Boltzmann weight, because in analogy to physics, where the Boltzmann distribution is an equilibrium distribution of certain Hamiltonian, certain energy function. And from the Boltzmann weight, just like in physics, we have this quantity Zn called the partition function, or the evidence, or the marginal likelihood, or the normalization constant for the posterior. Many names, very important, right? It's defined as the integral over the Boltzmann weight over the entire probability, over the entire model parameters. Right. Okay, and the posterior distribution is given by the Bayes theorem and written in our preferred notation using the energy function and things like that. It's just it's in this form, and I hope you are familiar with this form now. Yeah.
How should I kind of think about, when I think about the partition function in physics, I think of it as being kind of a ratio between the points at the lowest energy and like all the points?
Yes. Yes.
It's difficult for me to look at that equation and see how to kind of equate that to that thought.
Oh, can you repeat that description again? You were saying that when you think of partition function in physics, you are talking about sort of the...
I think about the ratio of the points at the lowest energy level.
Free energy, right?
Yeah. To all of the...
To all the others.
Yeah.
But that is the Boltzmann weight. what you just described, even in physics, if I remember correctly, it's the Boltzmann weight.
That's not the partition function.
That's not the partition function. The partition function is the sum. So in physics, you will have
the partition functions like the denominator of Boltzmann weight or something.
Correct.
Okay.
Yeah. So you have you have finite states. Then and this is the energy of that state. You might want to sort of normalize that by the ground state energy. And then the partition function is the normalization constant of this, which is sum over all states of the numerator.
Okay. Thank you.
That's a partition function. It's typically a temperature, beta, there. Yeah. Okay. All right. So we talk about learning machine, and this is one learning machine, right? So in SLT Layer 1, we talk about MLE, which is just finding the maximum likelihood. Or you can use other kind of point estimator like SGD, not quite MLE, and they have their own properties, right? And this is just another learning machine, something that takes in your model and your data and produce something that makes prediction. This is the Bayes predictive distribution. This is known as the Bayes predictive distribution. And the way it makes prediction, there is not much of a process of learning here. The way it makes prediction is every time. So if you ask it, what is the probability of X? It will try to ask the opinion of all the distribution in the model, what their opinion are for the probability of X, and then just average over them, but weighted by their historical performance, like their performance on historical data, which is given by the Bayes theorem, which is given by the posterior. Okay. All right. Okay. I want to note here that if you go and search for Bayesian inference or Bayesian method, I think the first hit you will get is not the predictive distribution. You will get the maximum a posteriori estimate, which is very different from this, right? That is closer to MLE than it is closer to this. Okay. Just as a note of caution, right? So error or performance measure is just as always, is the thing that you produce, the thing that the learning machine produce, the thing that is making prediction, and how far away in KL divergence distance from the true distribution. This again, everything on the slide that involve Q is a theoretical quantity. It's a theoretical analysis of how good something is. It's comparing to Q, which we don't usually have. If we have that, we don't need learning. Okay, so there is a Bayes generalization error, BG, and then there's a Bayes training error, which is just replacing the expectation over Q by the data average. We won't touch on this much. I think there's a lot of questions and comments when we go through the primer that we talk about the free energy a lot, but we never talk about generalization error. Free energy is not the generalization error. It doesn't tell you how well this machine generalized, but it is related to it, right? Perhaps also as a note of looking at SLT as a big picture. So results that is related to the Bayesian, that's related to the free energy are kind of more about the model than it is about the Bayes machine itself. It's telling us where the singularity are, telling us where the posterior concentrate, and so on. But then when you want to talk about the property, the generalization property of certain learning method, it is then you need to talk exactly about the Bayes machine, right? Okay, just a quick sort of addressing this point. There is I frequently get comments on why do we use a Bayesian framework when it's so computationally difficult. Some tongue-in-cheek answer would be there are statisticians outside of machine learning, right? That's working on smaller dimensional models, and that you can actually do MCMC and get results using Bayesian methods. Okay, and look at all those physics connection that Jesse's talk mentioned. And it is a perfectly fine learning machine, and the theoretical structure is interesting. But really, the answer here is that we are not, SLT is not just looking at Bayesian learning. It is kind of giving us insight into the model itself. So sometimes I would like to stratify results into a few layers. There is the layer of, is this result about the model itself? And then the second layer will be, is this result about using the model to learn a certain learn certain data? You can have a model and you can apply it to different domain as long as it is a model on the same kind of space, right? The same model can be used on MNIST encoded as real vectors of real numbers, as well as something else, right? And then finally, there is final layer will be, is this result about specific learning machine, right? Where you have used the model, used the data, and then produce some prediction. Those three layers are kind of very different. Today we are more concentrated on sort of properties of model. We are kind of in the second layer. All right, so to do theoretical discussion, we introduce some normalized quantities. So normalized quantities, this is where objections about whether or not Q, the true distribution, is a real thing, comes in. Our theory depends on having a Q. It's all about you observe data and then you ask about its future prediction performance. But if you want to say something about how well this learning machine will approximate some true distribution, this is where you start to compare the thing you get to the true distribution, right? And these quantities are normalized by the true distribution. For example, the likelihood function is normalized by the empirical entropy of the true distribution, so that this is very much akin to zeroing the ground state energy in physics, right? That's like akin to the ground state energy. I only say akin because this is a stochastic quantity. And then once you've done that, the Boltzmann weight, you replace all the L's with K's. Inside Z, the partition function integral, you replace the L's with K. The free energy is negative log of the partition function, and the normalized one is just a negative log of the normalized partition function. The posterior remain the same because the normalization constants sort of cancel out each other. Okay, so that's one transformation we're going to do. The next transformation is important for this talk because we're going to separate the effects, the dominant effects of geometry from stochasticity, right? So what that means is that to prove results in singular learning theory, there are effects that comes from geometry. That's what we're going to focus on today. And then you need to separately show that the randomness that comes from the fact that you are randomly drawing data. These functions, as we said before, these functions are actually random functions. They are random variables that depends on the data. Right. So we kind of replace them by their average and study those first and check later on that the fluctuation from their mean doesn't affect the leading order term. Okay, that's kind of the program here. Okay, so this is how I arrange these quantities in my mind. This is informally how I arrange them. So these are, so on the top left, you have things that are actually observable. You can actually go out there with data and actually compute these quantities, right? And then for theoretical discussion, we normalize them by comparing them to a truth. That's for analyzing how good our model is. And then for this, for the bottom right, that's what we will focus on today, just to give you an idea that what is the effects of geometry in for our model. Any question so far? Yes.
When you call it annealing, why do you say annealing?
I put a quote there. I am actually not very confident about that name is really good, but this is kind of a gesture towards the statistical mechanics of disorder system, where there is it's like in alloy you have say steel, you have ions, and then you have randomly put in carbon atom, and then for so the carbon atom is sort of like your data, the randomness where you put it. Okay, and then Kn is kind of the energy of a fixed carbon placement. But if you want to talk about the property of all steel, you will want to average over all possible placement of those carbon atom. And then in sort of in annealing, an anneal average is like you allow, while you are doing your averaging, you allow those random variables to co-vary as well. Okay, I'm not very confident about that. This is like an exact, but I'm just going to say that this is, I'm taking out the randomness at the moment. Yes.
This might be really done, but top left is observable.
Yeah.
What's the prior?
You design your prior.
You just put it in.
You put it in. Yeah, prior is something you design, you come up.
And you observe. Yeah.
Yeah, everything else, and model is also something you come up. There is a form, neural network or something, and everything here are quantities you can actually compute in with. You get floating point numbers from this. You can do MCMC using these. Yeah. Yes.
Just making sure I don't get lost in the notation. Can you just say again what each letter is?
Okay, right. This will be yeah. So okay, so
L is loss, right?
L is the negative log likelihood. Negative log likelihood, right?
Okay.
So
is it reasonable for me to think of this as
yes,
loss?
yes, yes. Yeah.
And W's are weights.
W's are weights. Yeah. Parameters.
E is some constant that I don't care about.
E that's just exponential. Yeah. Yeah.
Some constant I don't care about.
Sure.
It's halfway between 1 and infinity.
Yeah.
N is the number of actual samples we have in our data set.
Yep. Little n is data set size.
Yep.
And that's an important quantity because we are going to, most of our results are asymptotic in n.
Yeah. F is our free energy.
F is the free energy. Z is a partition function.
Z's the which is kind of
It's the
I'm still having trouble. It's kind of what I should think about when I think about the partition function.
It will be probably be clearer.
Okay. And what's
Later.
What's the difference between K and L?
Okay, let's talk about the difference between K and L, not the K and L. K, so L, L is the likelihood function. L would, so in this situation, L would be the X, right? So it's the loss without the stochasticity, without the randomness, right? And K is just L minus its minima. So that instead of talking about optimum, we talk about zeros.
Okay. So it is so in the case where the optimum is achievable, then K is just equal to L.
Optimum is always achievable. If you assume that the parameter space is compact, there's an infimum, just minus that.
Okay.
Yeah. Okay. All right.
You don't think K and L is the entropy of the true distribution.
Yes.
Because even if you know the true distribution perfectly, you still can't predict.
K, it will turn out that K is the KL divergence between model and the model at W and the truth. Right. So K is always greater than or equal to 0. Right. Yes.
Why is there an independence in the if then
guess the same rules?
There's still an independence. So for example, these are e to the negative n K of W dw.
Oh, yeah.
Okay,
Sorry.
right,
yeah.
right.
Yeah.
We are not sending it to infinity yet. Okay, so the goal today is to focus solely on the bottom right to build intuition on how singularities affect our model, right? We are focusing on this integral that involves that k, okay? The goal here is to get a visceral understanding of the effects of geometry. I highly recommend that if you can follow along with pen and paper, or at least just do the maths in your mind. There's a lot of integrals, so I recommend that you do that. Okay. Okay. So the goal is kind of to understand the free energy formula, and Liam is here with apology. That's a minus, right? There's a typo in my SLT last SLT low lecture. That's a minus sign, and it was hopefully you will see that it is actually a minus sign in the full proof. Okay, so we are mainly concerned with only geometry, not the randomness in this lecture. Okay. Okay, so we'll go up in level and to point out the different ways that we can introduce degeneracy. Right, we start with the regular model where things are not degenerate, and here we will do some integrals. We'll do integrals for the rest of the talk. Okay, all right. Okay, so this is a case where your k of w function is w squared, right? So if you want a concrete model that leads to this, let's just think about linear regression plus noise, where the noise is Gaussian. Okay. So if you compute the k if your x sample is sampled from a uniform distribution, impure sample is sampled from a uniform distribution, then this will be a quadratic potential, right? So this is, in physics, this is a simple harmonic oscillator, right? Okay, and as you can tell, I don't really care a prior, set it to uniform, okay? And as you can also tell, I don't really care that it is a prior. This is a non-compact space. I'm setting it to a uniform. It's not normalizable, right? So, but I don't care, right? Okay, so we are, in this case, what is our normalized z function here? Integral. So we have integral over r e to the negative n w squared. Prior is constant. Okay, that integral, right? Okay, that integral is these things. We want to know what is the asymptotic behavior of this integral as n goes to infinity, as n gets larger and larger. Well, this is the image of how that goes. So you get n equal to 1, and it gets more and more concentrated as n goes to infinity. So that's n equal to 100 for the yellow in the middle. And you are probably familiar with these shapes. These are just the Gaussian curve. This is a Gaussian integral, right? And Gaussian integral, I hope that I can just quote the Gaussian integral result. This is just equal to okay. I mean, so e to the negative n x squared plus y squared dx dy over r squared over the plane is equal to.
I want to say this talk is a lot closer to how my students think math talks are going to be when they're like freshmen than a lot of talks I've been to. We're just going to do integrals for the rest of the talk.
Yep. I mean, it's called SLT low road, right? It's meant to be giving you all the nitty-gritty detail, right? This is 2 pi. Am I going to miss a pi somewhere? No, that's fine. Yeah, that's fine. Okay, so it's 2 pi 0 to RDR, change of variable. I'm not going to do that. Okay, so this is pi over n, right? So this thing up here, which is the square root of that, is root pi on n. Okay, this is irrelevant stuff. Let me delete that. Okay, so what is Fn in this case? This is our kind of first result. that is statistics sort of relevant. So Fn is negative log Zn. That's half log n minus half log pi. Okay, so recall that we have sort of normalized by the nth order term, the order n term, which is the term that determine how much things fit, right? And this half here is important. This is equal to d on 2, where d is a dimension of the parameter. In this case, it's 1. This is the result coming from the Bayesian information criterion, right? The BIC, right? BIC says that if you want to select model, like you are selecting using the free energy criteria, for example, you select model that fits well, and you penalize it by d on 2 log n. Yep.
To be incredibly pedantic, it's not just that one half, right? It's both of those one halves.
Nope, it's just that one half. It's just that one half. Okay, I'm going to start calling everything else junk in a moment. Okay, all right, I will keep going. Okay, so higher dimension. No, I think he's talking about the other half log pi. That term. That does not become the that does. Yeah.
So
Okay.
it is both ways. It is both ways.
Yeah.
But the other term is lower order. It doesn't depend on n.
No,
Yeah.
That's fine. But you there were two one halves in the formula, and you were pointing at one of them.
Yes.
That's why I said it's being
Yeah.
pedantic, because
Okay. Cool. All right. So higher dimensions, I can only plot up to 2 dimensions. So this is just classic potential well. The thing that you think about when you think about regular model, ball, right? Or if you want to generalize it a little bit, sort of ellipsoid in higher dimension, you can have so this is kind of the kind of potential in higher dimension. It's just some sums of squares, or you can have it becomes ellipsoid, where you the lambdas are greater than or equal to 0. Okay, so let's do so that integral, so e to the negative n, so nkw. So these looks like multivariate Gaussian. They are still going to become sharper and sharper at the same rate. Right. Okay. So this is easy. This is just the previous integral, but they all factorize. Right. And that is just root pi over n multiplied by root pi over n over and over again. And if you have lambda j's, okay, let me use a different color. If these are modified by lambda j's, so if you think about what lambda j's is doing, is modifying the curvature near the minimum point, right? So it's precisely the curvature, right, in the principal axis directions. So you get lambda j's, and this become, okay, what does it become? It become pi on n d over 2, 1 on root lambda 1 ... lambda d. Okay, so now I'm going to talk about, so let me write it up here. So what does the free energy look like in this case? We get d on 2 log n, that's the BIC term again. We get, like you said, d on 2 log pi plus a half sum over log lambda j's. Okay, and we are saying that the lambda j's are all greater than 0, in fact.
That integral product dwj.
Thank you. I'm so glad people are following the actual calculation. Is that a question? Okay. Yeah. Yep.
Before you finish with the slide, I wanted something else.
Okay, so I'm about to say something. So what was these lambdas, right? If you have an arbitrary function and then you diagonalize, you choose a coordinate such that its Hessian is diagonalized, you get precisely this form. So these lambdas, this product of lambda is the determinant of the Hessian of the function at the critical point at the minima, and that is related to the Gaussian curvature, right? So if all the lambda j's are greater than 0, then there is a minimum one which is also greater than 0. So these things, these logs of that, are just a bunch of constants, right? So some over them still a constant. It's all lumped into this this constant term. They don't vary with n. As n goes to infinity, if you want to do prediction on what the free energy is, if you want to calculate the value of the free energy, it's not sensitive to the curvature. Okay, right? So okay. Yes, what was your question?
I was like on the free energy. So like if this was say a singular model, would lambda be like the beyond no log n term?
We'll get that. Yeah, we'll get that. Yes.
Can you go back a couple slides? Stack one more. Okay, yeah. Okay, then forward. Yeah, and then forward back, forward slides.
Okay. Sorry.
Okay, yeah, no.
No question? Okay.
Just want to make sure that
Okay.
I know what bubble order.
Okay. Glad you are actually following the competition. Yes.
You've written down the gateway time.
Problems when there are zeros. That's okay. That's the next level, and let me just finish this level. Right. So the general result in this area is just using Laplace approximation. Right. So if k is a sufficiently smooth function from R to the d, and it has a unique global minimum, so in our case, this is so our k of w is greater than or equal to 0, and it is 0 at the true parameter. So it translates to having unique 0 for a learning machines k. And if the prior doesn't just kill that, is not supported at that global minimum, we want the prior to be supported at that global minimum. As long as prior doesn't kill that neighborhood, then you have this result, right? Which is just what we were talking about before. So this is 0, so that goes to 1, as what we said. Prior just contribute a constant term, and then there is this determinant of the Hessian. That okay. So so for a regular model, okay, there is also a sort of a technical condition where we need phi to be compactly supported. We kind of want to avoid the situation where that is a global minimum. It is unique, but we don't want sort of like a sequence of local minima that sort of converge with. Just a technical condition, right? So in the cases where Laplace approximation applies, you have your free energy being d onto log n plus things that are all order 1 that doesn't depend on n. Okay, including the Hessian, the determinant Hessian, the curvature part. Okay, so we have some observation. So this is what we get for our free energy. If you remember that there's a normalization term, so this part is the BIC, right? Okay, so I want to also observe that it is not very surprising that geometry hasn't played a big part in regular learning theory. There is just one kind of geometry to consider, a bowl. The only thing that is changing between different bowls is the curvature, and the curvature does not affect the leading order term. It affects the constant order term only, right? Okay, so the sharpness it's this term sharpness is defined in the literature in various form. It might be the maximum of the lambdas, the maximum of the eigenvalues of the Hessian, or the trace, the average curvature and things like that. That doesn't affect the main order terms. Right. Even if we have multiple isolated global minima, if we have multiple balls all touching zeros, right, they may have different curvature for each of those global minima. You can apply Laplace approximation to each of them. The one with the sharpest would contribute the most, but it doesn't affect the leading order term is still d on 2. Yeah, it's still d on 2 log n. The widest one contribute the most. Yes, correct. Yeah. So between that and that, obviously that contribute more to the partition function. Thanks for correcting me. Okay, let's go up to level 2, what we call minimally singular. I kind of want to emphasize that this is kind of just an intuition pump. Regular model. This is minimally singular. We are stepping up the degeneracy just by 1 bit. We're not at the full generality yet. If you and this is just a case to illustrate a kind of the degeneracy that you could introduce. This kind, right? Here we have W being in R2, but it only depends on one of them. So it looks like that, right? The potential looks like that. There is now we don't have a unique global minima anymore. We have an entire line of zeros. We have an entire line of global minimas, right? Okay. Yeah. So W2, you might call it a kind of a free parameter. Right. Okay. So in that case, you can do the integral and W1 squared dW1 dW2. Okay. Immediately, I already have a problem. So dW2 is just by itself. That thing, the dW1 integral is what we have before. Aha, I want to integrate over all of R. That's infinity. So immediately we have a problem with non-compactness. I'm going to change that to, so not compact is a problem. I don't have a prior for that, right? Yes. So one way to do that would be either to restrict your parameter space or just have your prior to be supported on a compact set, or have your prior decay fast enough that it's integrable, right? Decay is like a Gaussian, for example. So if I change my parameter space to that, that's fine. So the upshot is that it is just a constant. And this is, again, root pi on n. So the constant only, again, modify the lower order term. Okay, right. So but you also could have this kind of scenario in which you it's not quite a free parameter. This is still where's W1? So W2 equals 0. So W2 equals 0. So this is still the line of global minima. And if you look at its Boltzmann weight, you can see that that entire line is where you want the integral to occur. But the factor is also affecting the thickness at various different points. So W1 is not quite free, but it might as well be, right? So if you look at the integral, it's yep. So you get, okay, you can apply the Gaussian integral formula again. So the dW1, so this will be root pi on n, except you have 1 square. Okay. Again, you need compactness, otherwise that doesn't converge. Right? It's a order one on W. It's W to the minus 1 order. That doesn't converge. But if you have compactness, this is just root pi on n and some constant, right? Similar thing. Right. So the generalization we have just made is that we have gone from just now, you have things, you have critical points that are non-degenerate, right? Where that just means that you are at a critical point, your Hessian is positive definite. Your Hessian is definite for general function. For our function where our k function is always greater than or equal to 0, it's just positive definite. The Hessian there is just positive definite. What that means is that you can do the change of formula such that if your change of coordinate such that your function in that coordinate is expressed as sums of squares, right? But we have now generalized to functions where those functions are called Morse functions. The critical points are non-degenerate. But then we are looking, in this case, something called a Morse-Bott function. That just means that the set of critical points of F is not necessarily sort of those discrete ones. They can form submanifold, smooth submanifold. They can be of distinct different dimensions. So the critical point of F could form something like that, could form a line, could form a point in 2 dimensions, right? Okay, so if those things are smooth submanifold, so nothing like that allowed, okay, and that the Hessian, not the full Hessian, but the Hessian restricted to the normal direction in those on those submanifold, if those in the Hessian in those directions are non-degenerate, then you get something called the Morse-Bott lemma, where in some coordinate you can make a change of coordinate such that your function in those coordinates is expressed as sums of squares, right? Ignore the n-negative part because we don't need them.
Can I ask a really stupid question?
Go on.
Is a Morse-Bott function a generalization of a Morse function or a specific kind of Morse function?
Generalization, right? If you interpret these symbols in their most general form, like a point is a smooth submanifold.
Proper Morse function is a sub-kind of Morse-Bott function.
I think so. I don't think I missed anything. Yeah. The normal direction would just be every direction if your critical submanifold is a point, right? For example. Yeah. Okay. So this is one kind of degeneracy. So this case, this minimally single case is not just where you have 3 parameters, right? You add parameter to a model that if you change them, it doesn't matter. That doesn't change your prediction at all. Those it's not just having those line or entire plane where your parameter doesn't matter. You can also have submanifold. As long as they are smooth, you are still in this minimally single case, and in this case you can fix Laplace approximation. Laplace approximation doesn't work in this case, right? Why? Because in Laplace approximation you have something ... over the determinant of the Hessian. The Hessian is there's entire there's a direction where you can walk it doesn't change anything. It doesn't change the value. The Hessian is singular. There are 0 eigenvalues for the Hessian, right? The Laplace, this is 1/0, just doesn't work. But if you restrict your Laplace integral, so you integrate out all the tangential direction to your critical submanifold, and then you apply your Laplace approximation to the normal direction, then it still works. But you have integrate out all the tangential direction. So the remaining thing is like d prime, where d prime is the number of normal direction, which is the co-dimension of the critical submanifold. That means that if the 0 set of your k function, if the minimum energy state forms a circle in 3 dimensions, you have 2 normal direction, then the d on 2 in your BIC need to change from 3 to 2. Okay. Right. Go on. Question.
Can you go back a second? Are we we going to care ever about the global properties of the C sub i's? Or do we only kind of just care about like locally they're this dimension and that's it? Like do we
So
care about, like,
we care about them locally, right? Why do we care about them locally? Because we care about the partition function integral,
Sure.
and we care about, as we collect more data, as n increase further and further, what is the behavior of the partition function, right? What is asymptotic behavior? And as n becomes larger and larger, so k is greater than or equal to 0, only the 0 set matters. Only the integral is concentrated around the 0 set, right? So those right, those kind of picture. If n gets really large, everything else that is not 0, k is not 0, there e to the n something not 0, and n is really large, becomes very small. So we are asymptotically, we are only interested in the neighborhood of what we call W0, capital W0, the set of zeros of k.
Sure, but do we care about kind of the global topology of that 0 set?
In this case,
like we've
no.
said we've got this connected smooth submanifold.
Yeah.
Whenever someone says we've got a smooth submanifold, then I want to know, like, do we actually care about like the topology of that manifold of these like C sub i's, or do we only care about the fact that it is a manifold, and like will we care about its Euler characteristic, or like
the only thing about the topology that
groups or anything?
the only thing we take care about to do this integral, the only topology we care about this manifold are that they are compact.
It's just the fact that it's a manifold and
Yeah.
its dimension and it's compact.
Correct. Yeah. All right, so we can fix a Laplace approximation, and there's already a quite crucial observation here. The free energy and the generalization and the BIC, or any kind of information criterion you want to derive, even in this case that is not regular, geometry matters, right? And all these quantities depends on what kind of data you apply your model to. In the regular case, you have a model, your BIC, your information criteria, the leading terms of your free energy, does not care what you're learning, right? It kind of care about the complexity term, doesn't care. The first order term cares how much you fit, right? But that's kind of it, because only the parameter count matters in the regular case. Here, if you, for using the same model, same parameter count, if you are learning a different truth, if your k function changes, its 0 set changes, its codimension changes. You might go from something that is a codimension 1 thing to codimension 2 thing, right? That changes. So already geometry should play a role in models like this. Okay, Bayesian information criterion won't work until you account for the free dimension. The free, I say dimension, but they are not, right? The tangential direction in your critical submanifold. Okay, so there is kind of a generalization of the idea of flat and flat basing. So you could have, let's say, okay, why is it not? Let's say this is your critical submanifold, and so the contribution to your integral is different at different point, because you could have could be very flat there, you could be very sharp there, right? And those different parts will contribute differently. But that is still only moving the needle in the lower order term. Okay, you have sort of a whole manifold idea of sharpness here. Yes.
Can you go back to slide? One more. Yeah. Okay. The Morse function slide. Yeah. So it's a theorem, right? That basically But basically all functions are Morse functions, right? The set of non-Morse functions are measure zero on the side.
Yeah.
If we look at the non-Morse functions, then are the Morse spot functions kind of also kind of dense within that? Like are most of the ways for a function to fail to be Morse leave it Morse spot?
I don't know about the Morse bot case, but I can sort of say something about the all function almost all functions are Morse case.
Sure.
The reason almost all functions are Morse is because if you have a degenerate critical point, you can perturb it a little bit. So the thing that so this is a degenerate x to the 4 potential. Perturb it a little bit and it looks like that.
Yeah.
Right. Okay. That is not to say that if you start out with an x to the 4 case, you can just perturb and just analyze non-degenerate singularity, non-degenerate critical points. The reason is that the close by Morse functions have their critical points almost touching.
Yeah.
Right? Your gradient descent, your integral around here, you should analyze this case to study that case, and then you don't know how far you're perturbing, right?
Sure.
Right.
Yeah, I mean it's very kind of like, I don't know if it's literally related or it's kind of spiritually related to like transversality or something, right? But
I would tentatively say that it is spiritually related first to transversality. I need to sit down and check conditions. Okay, this is another just perhaps eye candy minimally single case where this is the Mexican hat potential. But I'm going to skip that and go to the final level. Now we are introducing more kind of degeneracy. And hopefully this is indicative of the general case now, right? Okay, it is something like that. Okay, singular, we have been drawing pictures like that. Okay, but singularity or degenerate critical point is not just about having non-smooth points in the pictures that you draw, right? Even in one dimension, where you can't draw this crossing, even in one dimension, this potential W to the 4 is what we will call a degenerate critical point. And it has quite profound effect on the learning machine. So
is this the point where really we should be starting to talk about schemes rather than varieties?
This is the point where we start to talk about varieties rather than smooth manifolds. Yeah. Right. So
but like varieties don't notice.
Algebra varieties do notice that. So this is a different variety from this. W squared is not in here, for example.
Variety has enough different. Oh, sure. But the intersection, right? The intersection with, well.
I'm talking about ideals here. Yeah. Okay. So if you do that integral, e to the n w to the 4 dw, I can't rely on Gaussian integral anymore. Right. So how do we do that integral? Did I do that integral? Yes, I did. Right. Okay. So you do the substitution, n equal to w to the 4, and you notice that do the substitution. So this, I'm just going to integrate from 0 to 1. Okay, that's right. So if I'm integrating across all of R, sorry, I'm including across all of R, but that's the same as integrate half of R, and because it's an even function, I will double that. I do that substitution, I get e to the negative u, and I get the Jacobian, which is 4n to the quarter, and u to the, I'm sort of peeking there, du. Okay, so what do we get? We get 2 1/4 n to the 1/4 0 to infinity. Okay, some sort of interesting integral emerge. Anyone recognize that integral? The gamma function, right? So is 1/4 gamma function at 1/4, and using the gamma function property, that is just gamma at 1/4 plus 1. I'm just going to write it like that. And in general, this general thing, okay, so this is the W to the 4 potential, and its Boltzmann weight as n gets larger and larger. You will see that just now the Gaussian one is like that, right? It's very different. Its behavior is very different. The part where it contributes to the partition function, it contributes to this integral, it has much more state that stays relevant as n goes to infinity than x squared. Right. So if you are looking at W to the 2k, and where k is a really, really high number, this becomes like really, really flat, right? There's much more state below a level epsilon in, say, W to the 80 than W square. Okay. Right. Okay. Okay. Now we look at this. I promise it's a final case where I will do some integral, but it is sort of the hardest case. For people who have already gone through SLT Lau final lecture, SLT Lau 4, this is what we did the entire lecture for the fully general case, right? But here I hope to give you sort of concrete example of what those calculations look like. Okay, this is a situation in which we really need SLT. If you remember this general strategy picture, we need to bring in Maylin transform, and we need to bring in Laplace transform. Okay. Okay. This is what this potential looks like. We are going to do this case later, but I also want to show this case, right? So this is W squared and W1 squared and W2 squared. So that the zero set now looks like that. It does have a non-smooth point in the manifold sense in the set. The Boltzmann weight looks like that. Okay, that's when both of those coordinates, both of those directions have equal contribution, and you can also have a case where one coordinate is much flatter than the other one. In that case, you get a Boltzmann distribution that looks like that, where the flatter dimension sort of matters much more in the limit as n goes to infinity. Okay. I jump straight to that lemma, but okay. So the general strategy is we are going to start with the zeta function. I'm going to, without comment, I'm just going to follow the recipe. But if you want to know the discussion and the proof of all that, it's in the SLT Lau 4 lectures, right? Okay. So the idea is that we have a core observation that this is the integral that we want to study. It is the Laplace transform of something called the density of states function. And the density of states function Maylin transform to something called a zeta function. And a zeta function looks like that. Again, I'm ignoring the prior. Thank you, DW. Right. Okay, so Laplace and Maylin transform are invertible transform. You can either do them by inverting them using contour integral, or you can there's a lot of them already work out, and then you can look up the tables of existing transform, right? The point is though, this integral is really hard. You can try. I'm not going to try here. You can try. It's going to result in something called a singular integral, where you need to deal with different kinds of convergence. Okay, but the zeta function integral is really, really easy, and I will let you see why. Because, so let's do this case. So O raised to the Z, so 2Z, 2Z, dW. They factorize. So I'm just going to do it on the square. So they factorize to become this has become 1/2Z plus 1. So both of them have the same value. So this is just square. Okay, so this is on 0 and 1 square. I hope that's really easy. Okay, I'm going to write it in this form. 1/4 Z plus 1/2 square. Okay, so the zeta function is a function, it's a complex function. It's a complex function. So in its original definition, if the real part of Z is greater than 0, this is just a holomorphic function, because even though even though if K have 0, it's not a problem when the real part of Z is greater than 0. But for the real part of Z being less than 0, so you get 1 over something that is 1 over an integrand that is going to 0. That could create non-holomorphicity. But by doing this integral, we have seen that we have analytically continued this zeta function to a meromorphic function, and this only have a pole at 1/2, right? At -1/2, sorry. So, and it is an order 2 pole. Okay, those order and where the poles are is going to be important. Why? Because we are going to start here. We want to get here. We are going to do inverse Mellin transform back up to something we call the density of states, and then we're going to Laplace transform that. Okay, I'm not going to do the inverse Mellin transform. You have seen the contour integral last time. It was somewhat painful, but here's a theorem that does that. So I've just exhibited a function f of t. So if you Mellin transform that function, you get something that looks like that, right? So if a is 1 and lambda is 1/2 and m equal to 2, then we get our zeta function, right? Okay, so which means that function transformed to our zeta function. It means that the Mellin transform, inverse Mellin transform, get us back to that function, right? Okay, if you want to prove that, you can have fun with integration by parts, or you can just actually go to Wikipedia, look up Mellin transform, look at the table, and find this. Okay, so now that we have that, it means that the density of states, it's not defined in this lecture. Okay, so we sort of pattern match, right? We have a quarter from last time. Our lambda was 1/2. And then our m was 2, and in that there's m minus 1 in here. Our a was 1. Okay, so we get this. Okay. Oh, crucially, it's only this expression between 0 and a and 0 elsewhere. Okay, so to get back to our partition function, we do a Laplace transform of this. Okay, that's the Laplace transform of this function. And we evaluate the Laplace transform at n, right? That's the Laplace transform variable. Okay, that gets us to, okay, so this is only this expression when t is between 0 and 1, and it's 0 elsewhere. So our integral becomes going from 0 to 1, t to 1/2 negative log t e to the negative nt dt. Substitute tau equal to nt. We get, okay, now t goes from 0 to 1, so tau goes from 0 to n. That becomes tau on n to the negative 1/2. Okay, you can see where the asymptotic of n is creeping in here. So e to the negative t, and then negative log tau on n. There's a Jacobian of n there, d tau. Okay. All right. So I'm just going to write out the final. You can do this in. Yeah. Those are taus. Yeah. Okay. Right. Okay. So you get 1/4 root n 0. Okay. I'm going to go 0 to infinity, and then lump the minus. So there is the integral from 0 to n is just 0 to infinity minus the n to infinity integrals. I'm just going to lump all that at the end. So t to the tau to the half e to the negative tau dt minus. Okay, this one has a log n. Okay, plus a bunch of things that depends on c, that depends on n. Sorry, I'm just lumping them as using this cn. But all of them have the form n to infinity, and as n goes to infinity, they are actually going to. Are they order less than? Okay, they are at most order 1, right? Okay, so we have isolated the main order term, and that's the log n on n to the half, right? So if you take the negative log of that, you get, so the free energy Fn becomes a half log n plus, this is where the, okay, not plus, minus, sorry, Liam, minus log n plus a bunch of things that is sort of gamma function related, right? So those integral actually have values. Okay, so if you're wondering where the log n term comes from things like this. It comes from the order of the pole of the zeta function, which comes from how many of those coordinates contribute contribute the most and contribute equally. Okay, all right. So we have gone through sort of a baptism of fire here, just with sort of examples, and I hope that this gives some intuition. And I think one contribution singular learning theory can have is to sort of get rid of folklore that doesn't make sense, and start to sort of correct intuition in sort of everyday discussion, right? Instead of talking about the parameter count, we should talk about things like the RLCT, which sort of measure complexity in the sort of correct way. Okay, so what's not surprising us now? So now that we have gone through some of these examples for models that are not just regular models. So the free energy and generalization and a lot of other quantities like information criterion depends on the truth. And 2, it also depends on the model, like architecture of the model matters, right? If you are only using the regular statistical learning theory, what happens is that you'll be like, why do I need to consider CNN, convolutional neural network, for CFAR 10 if I just when I can just use the same multi-layer perceptron with the same parameter count? Their free energy to leading order term is the same. It's just d on 2, right? Okay, one might fit better. In fact, MLP may fit better. I don't know, but there is no difference if you just assume that regular statistical learning theory applies. You can't distinguish between the two of them. Right. In fact, if you only use, say, a BIC to choose model, you will never consider deep learning, right? No matter how well your so BIC, so n ln of the MLE plus a penalty d on 2 log n. No matter how well you fit your model, there is this massive, okay, 170 billion dimension onto thing that is penalizing your, that's telling you not to choose this model, right? So you might as well use a linear regression. It might have worse fit, but it doesn't have 100 billion parameters, right? Okay, so I kind of have a little bit of a personal gripe on these few points. Like I think a lot of us in the pre-2010s, for example, might have someone might have told us that, okay, you are using a machine learning model, like in that area you might be using SVM or decision trees or something like that, and then someone might come to you and say, don't use that model, because go and try to use that model in a, say, classification problem, and then just scramble all the labels. That's a random label. You will still get 0 training loss on that because your model is so expressive. But then your test loss is crap, and then that is overfitting. It's like the model can overfit, therefore don't use it. I don't know if you have encountered this kind of advice, but I had, not from sort of individual people, but it's kind of the literature is like cramming that down my throat, right? It's just not true, right? Those model SVMs, mixture models, decision trees, regression trees are very singular, right? How well they do depends on what kind of data they are learning. If the data is not learnable, it's a randomly reliable sample, or no model will do well, right? Singular or not. Okay. BIC doesn't apply. Different regions of W. So this is where I want to emphasize that the theorems that we prove, for example, the free energy formula that has, so this is the free energy formula that, okay, let me write out in the full stochastic glory. So this is not what we have proved today, or not what we have seen today, but we have seen the version in SLT Low 4. I keep on writing plus. So this formula only relates to the zero set of K, right? So all these quantities in these first few terms. So there are all the lower order terms, but these first few terms only depend on the geometry of W0, on the zero set of K, on the lowest energy state, right? It doesn't matter about how the model behave elsewhere. So even though it only matters how it behaves in the vicinity of the zero set, right? And in an arbitrary small neighborhood of the zero set, right? I'm talking about asymptotic result here. Be careful, because for different for n where the lower order term start, so there's a cutoff. So asymptotic result means that there exists n such that the lower order term is very small, doesn't modify your the thing you compute up to certain decimal point, for example. But for that n might be small enough that you might some other places with more singular with more contribution for lower order n might kick in. This is where the story about phases and phase transition comes in. That's see Dan's talk in SLT high. Right. But asymptotically, these few terms only depends on W0, right? So I say it depends on the geometry of W0, I mean the geometry as a variety, right? Okay. Okay, that's all I want to say. And so continuing from this lecture is the proof that goes through all of this, including by putting back in the stochastic effects. That was from conversation with Xiaowei. That seems to be sort of a non-trivial part. That seems to be a difficult part. This is results that that might might have been well known to geometers before singular learning theory. But the relationship of these geometrical results to statistical learning theory is kind of a big leap forward for statistics and machine learning. Okay, that's all. Any question? Yes.
So as part of this, right, we were sort of taking different transforms like Mellon transform, the Laplace transform, etc.
Yep.
The density of states.
Yep.
And I guess my engagement with these types of transforms is like they're a sort of trick that lets me solve differential equations. But the transform variables here are actually meaningful, and each of the transform terms have some sort of meaning. So can you say anything about what's like a physical or statistical interpretation of a Mellon transform or a Laplace transform?
The transform themselves have meaning. I dispute that. Okay, just okay. So we are used to sort of Fourier transform having very physical interpretation.
Yeah.
Laplace transform too,
yeah.
Particularly where it is used to solve differential equations and things like that. Mellon transform, I must admit, I don't know so much.
You said the Laplace transform you do think of as having a physical meaning?
Yeah.
Yeah, in certain situation. Don't grill me on that right now. Okay. I'm going to lump Laplace and Fourier transform. And also obviously these transforms are sort of related to each other. If you just do some I want to say straightforward change. But they are related to each other. Laplace transform is not going to do that live, but they are related to each other, right? Okay, but Mellon transform though, it has been used. So Laplace and Fourier transform are used in the physical sciences a lot. Mellon transform seems to mostly being used in the theoretical side of things, mathematics, and also theoretical computer science for investigating algorithmic complexity. And it's particularly useful to look at precisely these kind of problems where we want to turn a problem about asymptotics into problem about arrangements of poles of the zeta function of its Mellon transform. I'm hoping Dan would touch on that in tomorrow, perhaps, about the role of zeta, how that works in general. But you're right. To me, it's like an object, like a generating function in combinatorics that sort of encodes information that you want to elicit. And yeah. Other question?
It's going to be on Zoom shortly, and briefly demo a kind of fun visualization for the flow models of superposition. If I can.
Yeah. Speakers. Oh. So this seems to be a speaker.
Yeah. That's what? That's just
I think that's just a picture.
it could be
HTML.
could be everything.